Hello, everybody. So, today, as you see here, I'm going to be getting into physics, psychology, and discrimination. And you're probably scratching your head going, what is this guy crazy? I mean, that's a legitimate question on pretty much a daily basis. But all I'm going to be saying here is in the late 19th and early 20th century, we've got some really, really interesting things going on. And a lot of them fold into each other. And some are really great and some are really bad, and they all kind of bounce off each other. So let's get into it. Now, I have here it's about to get a little bit crazy, and indeed it is. You know, when we're looking at physics and psychology and things like that, what we are getting are some really dramatic new views of things. But at the same time, with these views are specifically going to challenge some views of the past that were kind of almost considered like sacrosanct, like Isaac Newton and Galileo, and those guys are going to be like, up for criticism and up for expansion. And it's really, really important to watch what these guys in science, particularly physics, do. Now, I have here, this is just a wonderful picture of the Solvay Conference of 1927, and you can read the name of all of these scientists, and I'm going to be talking about a number of them today. I mean, this might be the smartest picture ever taken by people in the history of mankind. It's absolutely wonderful, and we're going to talk about these people, but what you have is this collection of scientists that are going to be living at the same time and working and pushing each other, and you just get some wonderful things that are going to come out as a result of it. And one of those things is figuring out the atom. If you look on the left here, I have a list of guys: John Dalton and J.J. Thomson, Ernest Rutherford, Niels Bohr, and Erwin Schrodinger, who were all really crucial for allowing us to understand exactly what the atom is. The concept of the atom does go all the way back to the ancient Greeks with Democritus, but it really was starting with John Dalton in 1803 that really started to enunciate this idea of atoms and the concepts behind them. And then slowly but surely, with positive and negative charges, and then the nucleus, and how there's different levels of electrons, and then this whole idea of the clouds of electrons moving back and forth. And what you have is that by understanding the atom, it's going to allow us to get a deeper understanding of how the universe works. And two main things that are going to come out of this, both the work of the guys in quantum theory as well as the ideas of Albert Einstein, are really going to help us get a greater understanding of the world around us. And it's these guys who are figuring out the atom during this entire time that really contribute to everything. Because if you can't understand that base level, we can't go to the next high-end stuff that we have. Now, one of the groups of people, if you will, with Marie, are Marie and Pierre Curie, and she's awesome and he's cool, and these folks are incredibly important. And Marie, I like to point out, not that she's any smarter than Pierre, but for Marie to do what she did in a field where women virtually weren't allowed, like a woman physicist, are you crazy? And what she had to overcome was incredible, and she should always be respected for that. And a lot of times she had to work a little bit harder than everybody else. But the work of the Curies is huge, because I just talked about the idea of the atom. It is Marie and Pierre Curie who really discovered everything behind radiation. Okay, and also sadly their deaths as a result of radiation poisoning allows us to understand how atoms break down and energy, and there's so much stuff that we're going to gain from their work. They also discovered two elements, being radium and polonium, but their work is going to substantiate and expand a lot of the work of the other guys that I'm going to talk about, and is crucial to so many things that we do today, from X-rays and how we use those, which were really discovered by William Röntgen, who's another important figure in this particular time, and MRIs and all these different types of things that we use. A lot of that work can go back to Marie and Pierre Curie. All right, so look. I'm about to try to describe quantum theory to you and a variety of different things. I'm probably not going to get it entirely right. Quantum theory is a world-changing thing, and much of what we have discovered is real, and the idea of quantum theory is trying to understand the universe and how it actually works particularly at a subatomic level. I have a list of a variety of guys there that are really crucial for this, and you can look up their work, but let's just get right to it. So the basic idea of quantum theory is that the universe is made up of these particles, okay? And particles act in a variety of different ways. And one of the ways that we understand how particles act is that they actually move as both having the appearance of particles and at the same time moving as waves, which I'm going to get back to when I talk about Einstein. And our goal is to understand that how matter is formed and then how matter works, okay? And one of the ways that we did this was this idea of doing an experiment called the double slit experiment. And you can look up on a variety of different things, but basically what you had was a lead sheet that had two slits cut in it. And light, or specifically photons, were sent through it. And what you would do is that as the light went through, you would see a pattern over here of electrons or photons and how they hit, and you could see, okay, well, they're moving in this straight direction, they're moving through the slits, and the lead is blocking them, and so this would indicate that these are moving as small particles. However, what then was done is that they shoot electrons through the same type of thing. And the assumption was that one particle would appear behind the slit at a time. But what ends up happening is that they don't. What you get over here is an interference pattern, which makes it seem as if these electrons can actually travel through both slits at the same time and hit different spots at the same time. And what this kind of proves is that light, in this case as well as electrons, can move in these little packets of energy that are both particle-based and wave-based. Okay, and as we start to try to understand these particles, we get the development of Werner Heisenberg and his idea of the uncertainty principle. Because what happens is well, we want to now understand how particles move and why they move. Well, it turns out that if we want to measure location and speed, we can't actually do that. So if you want to identify where a particle is at any given time, you can do that. If you want to identify how fast a particle is moving at any given time, you can do that. The problem is that you can't do it at the same time because there's too many things going on. Okay, and what happens and what that means is that all particles, as well as us, have the potential to be everywhere and every when at the same time, and they actually don't really come into existence until we measure these things. That then moved into this idea that Erwin Schrodinger developed, okay, of this idea of Schrodinger's cat. And basically comes into this idea that if you put this cat in a box and that you have a container that contains radioactive material that is slowly going to decay, and when that decays, it's going to release a hammer when you have a certain amount of decay, which will release cyanide poisoning, which will kill the cat. It's really complicated, but what basically this figures out, if you will, is that everything has a potential to exist in a variety of different ways, as I mentioned before. Okay, that once the possibility of something exists, it actually can exist in the real world. And what happens is that the cat is both alive and dead in this box, because until you open the box, you don't know what it actually is. And this is a really fascinating concept that the quantum theorists are basically trying to develop, is understanding, where these particles are going and how they're going to get there. And it's interesting because it helps us develop a variety of different theories and really pushes our understanding of the universe, and in many cases how we feel that the universe itself was created. Now, the guy that's also working on other stuff at the same time that those quantum theorists are working on things is Albert Einstein. I have here Thinking, Thinking, and More Thinking. Basically, his big stuff is that he sat and he thought. He wrote equations, but he felt that equations shouldn't be too long, and it was really all about how he thought. One of the big things that he developed and actually discovered was something called the photoelectric effect, which specified with light that light exists as both a particle and a ray. He actually proved this, and that was really important for what the quantum theorists were doing. Okay, and this is what he actually won his Nobel Prize for. But really is what he is known for two things: the theory of general and special relativity. What he and what you need to understand before I even explain this stuff, guys, all of this stuff has been tested over and over and over again, and it's true. We call it theories because theories are tested, but this indeed is scientific fact. The idea is that he was looking at space, time, and gravity, and he looked at the work of um, Isaac Newton, and he realized that Newton seemed to be a little bit off about things. And so what he developed were a series of equations dealing with gravity, space, and time. Okay, and in fact, that gravity, space, and time are not separate. They're actually one thing. And this idea is called space-time. And space is actually curved. Gravity works in that larger bodies warp space with their gravity. In case you see here, Earth actually sits in space, and as I mess with my volume there, and it puts a depression in space because of the physical mass of it, okay? And what happens is gravity is when these large bodies warp space, they catch smaller things in that warp. So what happens here is we have this warp down here, you have the satellite, and what happens is if it gets too close, the satellite will catch and run around in this warped space. Okay, now one thing so gravity doesn't really pull anything, it more catches things. Now, this theory, one, allowed us to eventually understand and theorize black holes, which we can talk about later, but also it allows us to understand the curvature of space and use things for like satellites for communication and GPS. This is actually pretty cool. And so there's a practical side to this. Then you have the idea of special relativity, okay? In that, in special relativity, there is no universal state of rest, that all motion is relative, okay? Now, meaning that everything is kind of moving in a variety of different ways. And the whole idea is that the way that we observe things is how they are in nature. And so let me get this to you. The whole idea is that no matter how fast an observer is going, okay, the speed of light is the same no matter what, okay? It's 186,000 miles per second. That is the fastest anything can go in the universe. So that is your baseline, okay? Now, based on how fast you're moving, that people traveling at different speeds will observe things in different ways, but those ways are actually correct. All right, so if I'm going at 100,000 miles an hour and I observe trees looking one particular way and I make measurements on how fast I'm going and what the trees are doing, I am right because of how I am moving relative, hence special relativity, to them. If someone is going at 30,000 miles an hour, they're going to get different readings, but they're not wrong. They're correct based on their relative position. Now, what this also theorizes is that the faster that you go, time actually slows down. And I'll be talking in my classes on how this works, but this has been actually proven to be true. And the idea is that if you could indeed travel at the speed of light, that time would no longer exist for you. Kind of a cool thing. Now, what comes out of all of these things with special relativity is the most famous equation of all time is E equals mc squared, which E equals mass times the speed of light, which using that and other ideas of special relativity, it's going to lead to nuclear power and atomic weapons. And so these things lead to tremendous changes on how we look at things and how they appear to us and just how the universe works. Now, that's on the big physical scale of the minor and the major. But then what also kind of goes along with that is we're doing all of this thinking. So, how about we look at the brain a little bit? Now, let's talk about Sigmund Freud. And Sigmund Freud is an interesting man. He's seen as the father of psychoanalysis. He looked at dreams and hypnosis to get people to relax. And basically, one of his big theories and thoughts is these ideas of repression, that your mind blots out unsettling experiences from the past. But those unsettling experiences still become part of you and can run you. And then until you deal with repressed feelings, that it can cause you problems. Now, he had a lot of theories, and again, key thing theories, not a lot of data on the mind. And basically what he developed is this idea that your mind is made up of three parts: the id, the ego, and the superego. The id is the center of your unconscious, okay? And that you have things that you are not necessarily aware of that actually drive you to act in any given amount of situations throughout your life and throughout each day, okay? And that human beings direct their energies toward pleasure and away from pain. So we are going to do things in general that we are driven unconsciously to do things that we like. He called this the pleasure principle. And that can be things like lustful drives or appetites for things, but that as humans are generally, that's how we're driven, okay? Now, the other part is the ego. This is kind of the opposite of the id. This is the center of reason, and this coordinates your inner life in what he refers to as the reality principle, that the true pursuit of pleasure all the time is not feasible, so the ego will step in and reject certain pleasures so that we can function in society better with each other, so that we're not just driven on pleasure. Then you have the superego. The superego is your conscious. This is stuff that you're aware of. This represents inhibitions, moral values of societies, your parents, and basically your superego makes the ego keep the id under control. And he felt that a lot of these things were driven through sexual means. And that a lot of conflict in ourselves are conflicts over sexual desires and appetites and stuff like that. Now, as I moved on accidentally, the issue here, though, and things like that, he developed like the Oedipus complex, and that repression begins in childhood. Here's the good thing about Freud. Okay, psychotherapy, which is what he developed, probes deeply into your memory to try to retrace the chain of repression. And a lot of people get a lot of value today out of psychotherapy, that we need to take the time to try to understand our mind and understand why we do the things that we do. And if we can understand those repressed feelings sometimes, it can allow us to actually truly deal with it and take things out of the unconscious mind and bring it to the conscious mind. The negative part about him is that he really doesn't test anything. He really doesn't gather data. A lot of the things, especially kind of the obsession about sexual drives running everything, really isn't accepted a lot today. And in some textbooks, they include very little information from Freud. But I think Freud can be seen as a titan because he's the guy that pushed all these ideas out into the forefront. And better scholarship has been done after him, but somebody has to open the door sometimes. And Freud is that guy. Now, the other problem that we have going on here, though, is that so you have these new science ideas, and Darwin becomes more accepted, and we have all this other type of stuff, and then here's where sometimes science goes bad. Then you have people who believe in discrimination and racism, and what they start to do is try to use science to back up what they want as a narrative. Okay, so see how I pulled this all together? One of those ideas is social Darwinism, okay? And the idea of social Darwinism is that cultures that are being oppressed through things, say, as imperialism, which I've talked about, or racism, or discrimination against the poor, is that this idea that the reason why those groups are oppressed and that those groups are unsuccessful, if you will, is that they have not evolved to be what, say, Western Europe or the United States in the late 1800s was. And this, social Darwinism is one of like the purest examples of, I think, of science used in a way that it was not intended. And this is going to cause a lot of problems. I've already talked about issues with imperialism in the class and stuff like that, and it's going to cause some problems moving forward. One of those such things is racism. Now, one of the issues that we're starting to have at this time is a rise in nationalism and the possibility of what we call ultranationalism. So what you end up getting is that this idea of national or ultranationalism is that our people or race or country is better than everybody else. And the way that we're going to prove that is through discrimination. Okay, and through conquest. For instance, there was a group in Italy called the National Association for Italy, as we must teach Italy the value of international struggle, but international struggle is war. Well, then let there be war, and nationalism will arise, the will for victorious war, the only way to national redemption. Now, I'm not picking on Italy because Germany had it, and Britain had it, and the United States had it, and all these nations had it. Okay, and one of the ways that this became expressed was through racism, because what's going to happen at this time is racism is going to develop into a biologic thing. I have here this idea of Volkish thought. The idea of Volkish thought, that Volk is a nation or people or race, and that we, not me, but the idea of those folks need to do everything to benefit their race. And probably the best example of that was a man by the name of Houston Stewart Chamberlain, who was from Britain, who wrote a book called The Foundations of the 19th Century. And he really focused on the Germans, and this guy is seen as basically the precursor to Hitler, and that modern day Germans were the only pure successors of the Aryan race, who were basically Germans and Celts and Slavs and Greeks and Latins and Berbers, and that the Germans were at the top and they're the creators of Western civilization, and then everything else and all other groups, like for instance the quote unquote at the time the Negroes, are lesser races, and if you look at them biologically you see the perfect skulls of the Greeks and then the messed up skulls of the Negroes, which is actually completely false, and he compares them to chimpanzees. And one of the big groups that he goes after are Jews. He will create a system into which to try to prove that Jesus wasn't Jewish. But the big issue of what he pushes forth in this idea of enforcing biological racism is that these groups are biologically superior, and as a result, what we need to do is then protect civilization from lower races, which he referred to as Jews, Negroes, and Orientals, or Asian populations. He does go after Jews the most. And if you look on the right, this is 1933, in which people are measuring noses and facial structure. Houston's book really talked a lot about that as well, that biologically Aryans are structured better. And this is where, again, the whole thing goes wrong. And when we have science being used in a way to back up vile ideas of racism and ultranationalism and discrimination. And so we achieve wonderful heights in the late 19th, early 20th centuries, but sadly some of those great heights will be used for some of the darker periods in world history. Okay guys, so hopefully this all kind of came together here, and I'll talk to you in class soon.